Hello, everyone. In this session, we will introduce the growth of functions. We will see three different notations: big O, big omega, and big theta. These three indicators help us to compare algorithms. Maybe you can consider it's the representation of the upper bound of the algorithm or the lower bound of the algorithm, or the exactly measurement of this algorithm. So you will see this definition later. So why we need growth of functions to help us evaluate the performance of the algorithm? Intuitively, you can consider if one algorithm A performs like 100 operations and algorithm B performs 1000 operations, then algorithm A may be faster than algorithm B. And how we determine the operation number, for example, 100 or 1000, basically is directly related to the input size. If you have, for example, 2000 data or 10,000 data sample, then you will perform different operations. So basically, we can evaluate how quick the algorithm can solve a problem based on some certain amount of input. When the input size grows, then maybe the operation number grows as well. So once we can evaluate how fast this algorithm, the growth of function grows, then we can determine how fast the algorithm is. Okay, in this case, we can see the input size of n elements. Then we can have two different algorithms which use 100n squared plus 17n plus 4 operations. And the other only have n to the power of 3 operations. So based on the input size n, you can see we have two different number of operations for two different algorithms. So for algorithms, we only consider when n is very large, because when n is small, then maybe two algorithms are both very fast. It's meaningless to compare the speed or performance of the algorithm. So they will have significantly difference when the input size n is large. Okay, so in this case, we only consider when n is large for this calculation of the operations. So for when n is large, for example, when n is 10,000, then you can see n cubic is way larger than the first operation, 100n squared plus 17n plus 4. Okay. In this case, we can also see when n is small, such as n is 10, then you can see this algorithm, the number is larger than n cubic. Okay, so don't be confused. When n is small, you may see if we call this algorithm A, this is algorithm B. Okay, so when n is small, you may see the operation of algorithm A is way larger than the operation of algorithm B. So don't worry about when n is small, because we only consider when n is large for the comparison of the algorithm. Next, let's see the definition of big O notation. For f and g are functions from the set of integers or set of real numbers to the set of real numbers. We use f of x is big O of g of x if it follows the conditions. The absolute value of f of x is less than or equal to c times g of x when x is larger than k. So in this case, we have two constants, c and k. Okay, this inequality holds when x is larger than k, and f of x the value is smaller than c times g of x. Okay, so maybe we can use the following figures to see this phenomenon. Okay, we have f of x and g of x. Okay, so this is g of x, this is f of x. So when g of x times c, okay, then the curve becomes this. Okay, this is c times g of x. Then you can see when x is larger than k, c times g of x is the curve here. Okay, so you can see f of x is always under c times g of x. The value of f of x is always smaller than the value of c times g of x. Okay, so that's the reason we use the definition of big O, because we need to consider the upper bound of the function. When f of x grows as x getting larger, then it can always be bounded by another function, c times g of x. Then we can consider g of x is the upper bound of f of x when x grows larger and larger. Okay, so that's the meaning of the big O notations, or we need to consider the upper bound of a growth of the function. Then we can use the big O notation. In this case, we consider the worst case of the algorithm. No matter how fast the algorithm grows, it can always under the upper bound of the other function. So we can consider even the worst case, we can still approximately calculate the number of operations under some tighter upper bounds. Okay. So for big O notation, we call that f of x is big O of g of x, or you can see g dominates f of x. Okay, so if g is the upper bound of f of x, then we can see g dominates f. Okay, we can also say fx is big O of g of x, which means g of x is the upper bound of f of x. Then these two constants c and k, we call that weightiness of the function, because by the definition of big O, we need to identify the weightiness c and k. Then we can say f of x is big O of g of x. Okay, next let's talk about some important points about big O notation. Because just like we said, we need the weightiness c and k. However, it's easy to find infinity many pairs of c and k, because by these figures you can see when you choose k plus 1 and c, it will be another pair of weightiness. You can also choose k plus 2 and c, it will be the next pair of weightiness. So there are infinity pairs of weightiness. And just like I said, the big O notation, the correct way to indicate these relationships is f of x is big O of g of x. Okay, this means it's like a set or family. They both have the same amount or the same order of the growth of the function. So if you write f of x equal big O of g of x, this is incorrect, because f of x is a function, but big O of g of x is the measurement of the growth of functions. So don't write equal directly, but you can write f of x is big O of g of x. Next, let's see how to prove the big O notation. In this case, f of x equals x squared plus 2x plus 1. We want to prove it's big O of x squared. Okay, So let's clarify the meaning again. In this case, we can see f of x is dominated by x squared. X squared is the upper bound of f of x. Okay, so next, to prove the big O notation of f of x is x squared, we need to find the witness c and k. So in this case, we can see once we choose x larger than 1, then we can consider x is less than x squared when x is larger than 1. And of course, when x is larger than 1, then 1 is less than x squared. So we can replace these terms in the original terms of the f of x. X squared is smaller or equal to x squared plus 2 times x squared plus x squared. Okay, based on this inequality, then we can replace the terms one by one. Okay, so we can derive f of x actually is less than or equal to 4 times x squared. This is how we found the witness c, because 4 times x squared, so 4 is the witness of c, and x larger than 1, so 1 is k. Okay, so when x is larger than 1, then f of x is always smaller or equal to 4 times x squared. Then we can see f of x is big O of x squared. Okay, let's see these figures to understand the relationships of these functions. So here we have x squared here, and we have x squared plus 2x plus 1. Okay, so after we use 4 times x squared, then you can see when x is larger than 1, then f of x is always under 4 times x squared here. Okay, so we found the witness c and k as 1 and 4. Okay, of course we can find another pair of witness. For example, we can see when x is larger than 2, then 2x is less than x squared. You can choose x equals 3, so 2 times 3 is 6, which is less than 3 squared equals 9. Okay, and 1 is also less than x squared when x is larger than 2. Okay, so we can replace 2x and 1 by x squared and x squared. So totally we will have 3 times x squared. Okay, so we found the witness when x is larger than 2, so k is 2. Then f of x is less than 3 times x squared, so c is 3. Okay, so we found another pair of witness. This can be also used for the proof for big O that f of x is big O of 4 times x squared. So in this case, we can see f of x by the previous example, x squared plus 2x plus 1, and gx is x squared. Then we show that f of x is big O of g of x. Okay, then we can also show that g of x is big O of f of x, because apparently you can see this is x squared plus 2x plus 1. This is x squared. Okay, so you can see x squared is always dominated by x squared plus 2x plus 1. Okay, so we can say x squared is big O of f of x. Okay, when two functions are big O of the others and vice versa, then we can call that the same order, because this means you are my upper bound and I am your upper bound. So the growth of these two functions are of the same order. This is one thing you can notice when you see the other exercise in these slides or in your homework assignment. Okay, next one, if f of x is big O of g of x and h of x is larger than g of x. Okay, so in this case, g of x dominate f of x and h of x dominate g of x. So h of x absolutely dominate f of x, right? Because it's a is larger than b and c is larger than a, so c is larger than b. Okay, so I think this relationship is very clear. Okay, so when we use the big O notations, we need to choose the big O notation as small as possible, because once we have a lot of tighter bound of functions, so tight functions is more meaningful. Okay, so don't choose very loose function or far away functions of this dominant function. Just remember this when you consider the big O notation. Next, let's see the example how we show that 7 times x squared is big O of x cubic. Okay, so in this case, we can see by the previous example, you can have the intuition first. We have 7x squared. So following the previous example, we can see it is big O of x squared. So in this case, we want to prove a looser bound. It's also big O of x cubic. Okay, so you can see x cubic grows faster than x squared if you plot these two functions. So in this case, we can see if 7x squared is big O of x squared, then for a fastly grows functions x cubic, then it will be big O of x squared as well. Okay, so after understanding these meanings, then the proof is very easy because we have 7 times x squared, so we can replace 7 as x. So we can write when x larger than 7, then 7 times x squared is less than x cubic. So we can take witness c equals 1 because we have 1 times x cubic and k equals 7. So we found the witness c and k. So we prove that 7x squared is big O x cubic. Next, let's see the general form of polynomial functions. We have seen the example of x squared, x cubic. Actually, we can write the polynomial function as its generalization form, anxn plus an minus 1 times x to the power n minus 1 and plus a1x plus a0. Okay, so you can see this is a general form of polynomial function. Once you choose different n, for example, n equals 2, n equals 3, or n equals 100, then it will be different degree of polynomial function. Okay, then this is a very important theorem. For these general polynomial functions, we can prove that f of x is big O of x to the power of n. Okay, so actually we just need to consider the leading terms. So the leading term is x to the power of n, so it will be big O of x to the power of n. Next, let's see how to prove this general form of polynomial function. Okay, remember by the definition of big O, we need to find the witness c and k. Okay, so let's rewrite these functions to discover how we determine c and k. Okay, by the definition, we need to have the form the absolute value of f of x is less than c times the absolute value of x to the power of n. Okay, so we apply the absolute value to f of x first. Then we can replace the terms to its general form of the polynomial function. Okay, then we can apply the inequality functions once we calculate the addition of all terms of the polynomial with the absolute value. Okay, then it will be less than we apply absolute value to individual coefficients. Okay, because an minus 1, a1, a0, the coefficients could be positive or negative. Okay, so once you apply absolute value to each coefficients, then the summation will larger or equal to the original polynomial function. Okay, next step, we can extract the common part x to the power of n for each terms. Okay, for the first terms, there are no x terms. For the second terms, once we extract x to the power of n, then we need to divide by x. Okay, because x to the power of n divided by x, it equals x to the power of n minus 1. Okay, so when we extract x to the power of n, the last term will be an divided by x to the power of n. After that, we have the common term x to the power of n. So it's just like the big O x to the power of n, right? If we assume x is larger than 1, then we can rewrite the following terms as a constant, because when x is larger than 1, then an minus 1 divided by x is less than an minus 1 because x is larger than 1. So a number divided by a number larger than 1, it becomes smaller, right? So this term will become smaller than an minus 1. And the last term and the resting term have the same results because we have a0 divided by x to the power of n. Once x is larger than 1, then this value is less than a0. Okay, so we can write each terms the summation of all coefficients an in an minus 1 to a1, a0 as the resting terms. Then these terms we can consider the summation of all terms is c. Okay, so we found the weightness when x is larger than 1. This is our k. And c is the summation of the coefficients. Then f of x is less than or equal to xn times c. Okay, so this is how we prove the general form of polynomial function with the leading term x to the power of n, which is big O of x to the power of n. Next, let's see some examples to calculate the big O notations. For example, to estimate the sum of first n positive integers. So when we calculate the summation 1 plus 2 plus 3 plus n, okay, then we can replace each terms by n to the less n. So we have the inequality. The sum of first n positive integers actually is less than n plus n plus n. There are total n different positive integers. Okay, so it's equals n times n, so it's n squared. So we have the big O notations because we have the weightness when we take k equals 1 and c equals 1. Then the sum of first n positive integers, which is big O n squared. Next, let's see the factorial functions. Once we use 1 times 2 times 3 times n, okay, we can use the similar techniques to replace each number by n. So we have n times n times n. There are total n positive integers. So it will be n to the power of n. This leads to the results. The factorial function, the factorial of n, okay, actually it's big O of n to the power of n. Next, let's see, use big O notation to estimate log factorial of n. Okay, this is very easy because by the previous example, we know the factorial of n actually is a big O of n to the power of n. So we can write the function factorial of n, which is less than or equal to n to the power of n. If we take log to both sides, then we can have log factorial of n, which is less than factorial n to the power of n. So this n can go from the logarithm operations. So we have n times log n. Okay, remember this because we will use the concept of log of the functions a lot. Next, let's see when we can have the relationships of two functions n less than 2 to the power of n. So you will see this inequality in section 4.1. Then it's easy to show that. Okay, so the big O of so n is big O of 2 to the power of n because n is less than this function. If we consider this f, this is g. Okay, then we can take log on both sides. Okay, so we have log n less than n times log 2. So log 2 you can consider is the weightness c. Okay, so actually we can derive the results. Log n actually is big O of n. So this is a quick estimate of the big O notations. We can see the detailed steps why log n is big O of n. If we consider the logarithm with base 2, then we can see this results because log n is n times log 2. Once we take the base is also 2, then it will be 1, right? So log n is less than n. When we take k and c equals 1 as the weightness. Of course, we can take other bases, not just 2. So let's see these relationships, this calculation log n. If we take the base of n, then we can rewrite this term as log n divided by log b. Okay, so when we write log n divided by log b, then we can consider log b as the weightness, right? Because this is a real number. So log n with the base of b, which is less than the constant c, c equals log b times n, right? So in this case, we have c equals 1 divided by b and k equals 1 as our weightness. Then log n with the base b is big O of n. Next is the most important slide in this section. We can plot the growth of functions of different functions. We have seen a lot of different functions. For example, we have seen the polynomial function, n squared. So you can consider n cubic, n to the power of 10, n to the power of 100. They are all polynomial functions. Then we have the exponential functions. Okay, remember the previous results? We have the relationships n is less than 2 to the power of n. Okay, so you can see the growth of the exponential function is larger than n. And we have the factorial function which grows the fastest. Okay, as n get larger, then this function grows way faster than the others. And we also have the constant function. So there are no variable n in this function. If f of x equals 1, f of x equals 100, we call this constant function. So no matter x varies, the result is always constant. So you can see we have a flat straight line here. Okay, so no growth of constant function. And we have n and log n. If you remember in previous example, log n is less than n. So that's the results comes from the previous example. The log n is big O of n. Then we can consider n times log n. Okay, this will be easy, right? Because once we know log n is less than n, then we can time n to both sides. So n times log n less than n times n. So this will be n squared. Okay, so n log n is grows slower than n squared. So we call this the most important slide of this section because after this, you can consider different categories of the functions. The first one is factorial function, which grows the fastest. Okay, so this is the first category of the functions, factorial function. Then the second category is exponential function. Okay, so exponential function means the variable n goes to the position of power. For example, 2 to the power of n, 3 to the power of n, 100 to the power of n. We call this exponential function. Then we have polynomial function. N to the power of 2, n to the power of 3. We call this polynomial function. Then we have logarithm function. Then we have constant function. Once you can divide different functions into these 5 categories, then we can determine its growth is easier. Next, let's see more details about these different categories of functions. Okay, the first case, if we consider the polynomial of n to the power of c and n to the power of d, when d larger than c, then we can see n to the power of c is big O of m to the power of d. Okay, the case is n squared is big O of n cubic, which is big O of n to the power of 4. Once n goes larger, then n to the power of d grows faster than n to the power of c when d is larger than c. Okay, this is how we compare polynomial function within the same category. Remember, we have 5 categories, so polynomial function is one category. We can between how fast the function grows between categories and within categories. In this case, we just compare both functions. All functions are polynomial functions, and we can still distinguish their growth n squared, n cubic, and n to the power of 4 or something. Okay, next, the log function is slower than polynomial function. we have seen this by the previous slides. You can see we have log n as category 4, which grows slower than polynomial function, which is category 3, right? In this case, I will show you something. If we have the power, for example, log n to the power of c, and a polynomial function n to the power of d, okay, then we can see no matter how the value c or d are, the log function is always slower than the polynomial function. For example, we can write log n to the power of 100. You can see 100 is a very large number, but the order is still less than big O of n. Okay, so this is how we distinguish between logarithm functions and polynomial functions, even though they have different powers c, d for this log function and polynomial function. Okay, next we follow the same concept because the polynomial function grows slower than exponential function. So once we have n to the power of d and b to the power of n, no matter the value d or b is, okay, it doesn't change the fact that polynomial function grows slower than exponential function. Okay, so in this case, we can see n to the power of 200, which is big O of 2 to the power of n, because this is exponential function. Okay, this is polynomial function. Polynomial function is always slower than exponential function, no matter the order is, the power is 200, or the base of the exponential function is 2, 3, or 4. Okay, the last one, if we compare the exponential function within the same category, then you can see 2 to the power of n, 3 to the power of n, they are both exponential functions, but the growth of 2 to the power of n is less than 3 to the power of n. Once we have the base b and c, once c is larger than b, then the growth is faster as c is larger than b. So based on this, you can see you can compare different function growth between different categories. And for some case, we can also compare the growth of functions within the same category. For example, how to compare the exponential function within the category of exponential function. Or we can also compare the polynomial function with different leading terms. Okay, so this is what we call within the category. And we can also compare the functions between categories. For example, the log family or the polynomial function, or the polynomial function compared to exponential function. Next, let's see what happens when these terms are combined together. If one function, so we have exponential term, we have polynomial term or constant term. Okay, this gives us very important theorem, theorem 2. If f1 is big O of g1 of x, and f2 of x is big O g2 of x, then the addition of both functions, we can calculate the max of g1 and g2 as its big O notation. Okay, so I think this is very intuitive, right? Because if we have f1 as exponential function 2 to the power of n, and f2 is polynomial function n squared. So if we have these combinations, f1 plus f2, we call that f of x equals 2 to the power of x plus x squared. Okay, then the big O of this function, you can see this one grows faster than this one. So when we calculate the big O, we extract the maximum of both terms. In this case, f of x is big O of 2 to the power of x. Okay, the corollary one is if f1 and f2 are both big O of g of x, then the combination of these functions will big O of g of x. Okay. Theorem 3 tells us if we use multiplications to combine these two functions, f1 and f2, which is big O of g1 and g2, then the combination of the functions will be big O of g1 of x times g2 of x. Okay, remember this theorem because it helps us a lot to identify the growth of different functions. Okay, let's see how we prove the combination of functions. So we just take the addition for example. Once f1 plus f2, then we need to calculate its big O of maximum g1 and g2. Okay, so even though it's the combination of functions, we can still apply the definition of big O notation to discover the weightiness C and K. Okay, so by this example, we know F1 is big O of G1, so we can write the weightiness C1 and K1 because this is given, right? And F2 is big O of G2 of X, so we can write its weightiness C2 and K2. Okay, so next we can write the combination of these functions f1 plus f2. So f1 plus f2 with the absolute value, then we can write is less than or equal to the absolute value applied to individual terms f1 plus the absolute value of f2 of x. Then we can use the given conditions. F1 equals C1 times the absolute value of G1 of x, and F2 is C2 times G2 of x when x is larger than K1 and K2. Okay, then we can write these terms is less than these terms. Okay, so when we get g of x as the maximum, but from g1 or g2, okay, because we have g1 here and we have g2 here. Once you can choose which one is larger, then we can write these terms will be less than g plus g times c1 plus g times c2. Okay, then we can combine the coefficient together, extract the common terms g of x. So the c1 plus c2 can be written as the constant c, and the k is the maximum of k1, k2. Okay, so this complete the proof when we can write f1 plus f2 is less than c times g of x. So g of x, remember, it's calculated from the maximum of g1 and g2, and k is also selected from the maximum value between k1 and k2. Okay, next let's see a lot of different functions, how to put them in order when we need to estimate its big O notations, which one grows faster than the others. So here we have 10 different functions. So you can see these functions varies a lot. We have, for example, factorial n. We have 8 times n cubic plus 17 n squared plus 1, 1, 1. Okay, so how to put them in order? So their big O can be increasing or decreasing order. Okay, next let's see how we solve this problem. Remember, we just partition or divide all functions into different category. So you need to go, we can go back to the figure again. Okay, factorial function grows faster than exponential function, and exponential function grows faster than polynomial function, then logarithm function, then constant function. So for these 10 functions, maybe we can put them into different categories. Then we can compare within each categories. Okay, so firstly, we can see F9 is 10,000. This is constant function. So we can see constant functions have no growth, right? No matter x varies, the value of the functions remains the same. Okay, then next will be log function. So we have two different log functions. We have three different log functions. Log n squared, n squared times log n to the power of 3. Okay, so how to consider log n? Okay, so if you remember, we have log n less than n from the previous example, right? And we can see from the previous 5 different categories, the category of log functions grows slower than n, right? So we can take log on both sides. So we can write log n is less than log n if we take log on both sides. So log n actually is slower than log n functions. So here we have log n functions to the power of 2. So you can see once they belong to different category, then no matter the power 2, 3, 4, it doesn't matter. Log n is slower than log n, right? So this is the second one, F5. Okay. So F5 is lower than F3. So next one is n squared. This is what we have seen in previous theorem. So once two functions f1 times f2, then they will have different big O notations. In this case, we have n squared times log n to the power of 3. So F3 absolutely grows slower than F6. Okay, so next one, we go to another category. Because we have n squared times something, we have a times n cubic, we have n cubic plus n times log n squared. Okay, so we can consider this polynomial function together. So here we have n squared times log n, because log n is less than n. So so n squared times log n is less than n squared times n, which is n cubic. So F6 is lower than F2. Okay, then how to consider F2 and F8? Okay, so we have three terms adding together, n to the power of 3, n squared, and the constant. And we have n cubic plus n times log n squared. Okay, so remember the theorem 1, when f1 plus f2, we actually extract the max order from each terms. Okay, so we consider n cubic is larger than n squared, so this term is useless. N cubic is larger than the constant function, so this one is useless. So the maximum one is n cubic. Then for f8, n times log n squared. So remember, log n is less than n. So m times log n times log n is less than m times n times n. So this one is less than n cubic. Okay, so if this term is less than n cubic, then this term is useless when it is added to n cubic. Okay, so in this case, f2 and fa, they have the same order. It's a polynomial function, n cubic function. Next, we jump to another category. The polynomial function is slower than exponential function. Okay, so here we have exponential function 1.5 to the power of n. So the other is 2 to the power of n. So you can see f1 is slower than f4 by this, if you remember. Okay, this one. Once we have different b and c in the exponential function, so if c is larger than b, then the exponential function grows faster. Okay, then we have 2 to the power of n times n squared plus 1, right? So we have another terms. Remember theorem 2, it tells us f1 times f2, the order is g1 times g2. Okay, so 2 to the power of n times n squared. So this one is larger than 2 to the power of n. So f7 grows faster than f4. Okay, so the last one is our king, the factorial function. So it's always faster than the exponential function, polynomial function, and the others. Okay, so this is the way we put different functions by its order when the function grows from the slowest to the fastest. Next, let's see the example when we combine different terms, how to consider its big O notation. Okay, so in this case, we have 3n times log n, log factorial n. Okay, so these terms, we didn't see it before. And we have the second term, n squared plus 3 times log n. Okay, so do you have any intuition? Because you can consider this is f1, this is f2. When we add them together, we need to determine which one is larger. And for f1, actually, it's two functions times together. So you can consider it's f3 times f4. And then we have f5 times f6. Okay, so for multiplication of two functions, we need to consider g1 times g2, right? So let's see, what is log n, log factorial of n? Okay, so if you remember factorial function, 1 times 2 times 2n, which is less than or equal to n times n times n. So this one is n to the power of n. Okay, so this is factorial of n. So if we take log together, then we have log n factorial n equals less than, this is not 2, this is n to the power of n. Okay, so we have n log n in the right hand side. So don't be afraid if you see very strange terms. For example, log of factorial of n actually is less than n log n. So for the f3, f4, actually we have n times n log n. And then for the f5 times f6, so we have n squared times log n plus 3 times log n. So you can see 3 times log n is smaller, is slower than n squared. So these terms can be ignored. So we have n squared times log n. So you can see for the first term f1, actually it's n squared times log n. The second term is n squared times log n. Okay, so when you choose the largest between f1 and f2, actually it's still n squared times log n. Okay, so this is how we determine the combination of all different functions. Okay, next let's see this example, x plus 1 times log x squared plus 1 plus 3x squared. Okay, so let's see how we derive this. You can consider this is f1 and this is f2, so it's addition, right? So we need to choose the maximum between f1 and f2. So how to compare f1 and f2? Which one grows faster than the others? Okay, so so for the f1, we can simply consider x plus 1 times log x squared plus 1. So when x times log x squared plus 1, this term is constant, right? So the constant is usually slower than x. Okay, so we can ignore 1 directly. So we have x times log x squared plus 1. Okay, the mouse is very difficult to use. Maybe we can see the derivation in the solution. Okay, so when we write log x squared plus 1, it is less than x squared plus x squared. Okay, so we can write 2 times x squared. Okay, then 2 times x squared can be written as log 2 plus log x squared. And log x squared, the power can be put in front of the log function. So we can write log 2 plus 2 times log x. Okay, so which is less than log x plus 2 times log x, because this one is constant. Constant is less than the log function. Okay, so we can write the log term together as 3 times log x. So actually, a log x squared plus 1 is 3 times log x. Actually, its order is log x. So you can consider when you have log x squared, log x cubic, or log x to the power of 100, it doesn't matter because its order is still log x. Okay, so once we know this one is log x, combining the previous term x, then we have x log x. The second term f2, we have x squared. So x squared is larger than x times log x. So in this case, we can determine the big O of the function is big O of x squared. Okay, so far so good. We have finished the introduction of big O notation. Let's review the concept of big O notation again. Big O notation just tells us the fx, the growth of function, can be dominated by the other function, g of x, for example. Then we can write the big O notation as its upper bound. F of x is bounded by the other function g of x. Okay, So actually we are discovering the upper bound of the functions. So when you are measuring the growth of these functions, once it can be always dominated by the other functions, then we can know at least what is the worst case of this algorithm. Okay, next we will introduce the definition of big omega notations. Okay, you can consider it's just the opposite of big O notations, because by the definition, if we can write f of x is larger or equal to c times g of x with the weightiness c and k here when x is larger than k, then we can say f of x is big omega of g of x. Okay, so once f of x is always dominate g of x, then you can consider g of x is the lower bound of the function f of x. Okay, so that's the reason we call it's just the opposite of big O notation, because by big omega we just discover its lower bound. When it grows faster, at least we can see it at least larger than the other function g of x. We call this big omega function. So it's easy to confuse these two definitions. It would be very helpful if you consider big O gives the upper bound and big omega give a lower bound of the other functions. It will be helpful to help you easily remember the definition of this notation. Okay, so let's see if f of x is big omega of g of x, which means f of x dominates g of x. G of x grows faster. F of x grows faster. G of x grows slower. Okay, and we have a very strong condition if and only if g of x is big O of f of x. Okay, so which means f of x dominates g of x. Okay, here we have f of x here, and we have g of x here. So since f of x dominates g of x, so you can say g of x is big O of f of x. So f of x is its upper bound. You can also say g of x is the lower bound of f of x. Okay, because the relationships is vice versa. Once A dominates B, then A is the upper bound of B. B is the lower bound of A. Okay, next let's see the example how to prove big omega notation, just like the way we did for the proof of big O notation. So in this example, f of x equals ax cubic plus 5x squared plus 7, which is big omega g of x. G of x is x cubic. Okay. So this one should be easy, right? Because f of x, you can see it has different terms. Okay, so if you actually plot functions, f of x is always dominate g of x, right? So we can see f of x is larger than 8 times x cubic. Okay, so this helps us to discover the weightiness. If you consider x cubic as g of x, then 8 will be the weightiness c for all positive real number x when x larger than 0. So k is 0 and c is 8. Then we can prove that it's big omega g of x. Okay, the last one is big theta notation. Let's see the definition. It's very similar to a big O notation. Let f and g be the function of the set of integer or the real numbers to the set of real numbers. Then f of x is big theta of g of x. if f of x is big O of g of x and f of x is big omega of g of x. Okay, so what does that mean? If x is g of big O of g of x, means f dominates the function g. Okay, f of x is big omega g of x. Okay, which means g of x. Okay, this one is incorrect. F of x is big O of g of x, means g of x dominate f of x. Okay, then f of x is big omega g of x, means g of x is its lower bound. So f dominate g of x. In this case, if f dominate g and g also dominate f, so which means they are of the same order. Okay, so we can consider the case we have seen before, x squared and the other polynomial function x squared plus 2x plus 1. Actually, you can see both functions of the same order because they are both, the leading term are x squared. Okay, so these two functions are of the same order. We can prove that f of x is big O of g of x. You can also prove g of x is big O of f of x. Okay, so we call that the same order. Once two functions are the same order, then we use the big theta notation to indicate this situation. Okay, so let's show that first n positive integers is big theta n squared. Okay, so remember when we prove big theta, we need to prove the first function is big O of the others, and it's also big omega of the others. Okay, so in this case, we need to show that 1 plus 2 plus n is big O of n squared. Okay, we have shown that before, right? Because 1 plus 2 plus n actually is less than n plus n plus n. Okay, so it's n times n is n squared. Okay, so we have shown that f of n is big O of n squared. Next, we need to show that f of n is also a big omega of n squared. Okay, remember the definition of big omega is the absolute value of f of x is larger than c times the absolute value of g of x when x is larger than k. Okay, so next we need to, let's see how we show that. Okay, so f of n is 1 plus 2 plus 2n. Okay, so once you consider this as the real example, for example, 1 plus 2 plus 3 plus 10, actually this one is larger than if we only consider the bottom half of this sequence. For example, this sequence absolutely larger than 6 times 7 times a times 10, right? Okay, so the bottom half of the sequence we can write actually it's n divided by 2 with the ceiling function, and this term plus 1 and this term plus 2 until to n. Okay, so we just choose the bottom half of this sequence. F of n is larger or equal to the bottom half of these numbers. Okay, and then this one is larger than if we replace each terms by n divided by 2 with the ceiling operation. Because you can see we have plus 1 here, and we have plus 2, plus 3, plus 4. So this one should be larger or equal to if we replace each terms as n divided by 2 with the ceiling operation. Okay, next we can calculate the summation of these terms. We have the terms n divided by 2 with the ceiling functions, and we have how many terms are there in the bottom half of the sequence? Okay, actually it's n minus n divided by 2 with the ceiling function plus 1, because the first element is this, right? So how many terms are in this sequence? It's 10 minus 6 plus 1, right? You can also write 10 minus the previous term. Okay, so its previous term is 5. So 10 minus 5. Okay, so the result is 5. Actually, we have 5 elements here. So this is how we calculate the summation, because we just write n minus these terms plus 1, just like this. It's the number of the total number of n divided by 2 with the ceiling operation. Okay, and then this term is larger than n divided by 2. Okay, so you can use the real example once n is 10. Okay, so 10 divided by n divided by 2 is 5. Okay, plus 1. So this gives 6. And n divided by 2 is 5. So 6 is larger than 5, right? Okay, so this is for even number. You can also replace n by 11. Okay, you can see the inequality still holds. Okay, so eventually we have n squared divided by 4. This gives our weightness. You can see the summation of first n positive integers, which is larger or equal to 1 divided by 4 times n squared. So 1 divided by 4 is our weightness C for all positive integers. So we complete the proof of f of n is big omega n squared. So once you can prove f of n is big O of n squared and it's also big omega of n squared, then we can see it's big theta of n squared. Next, let's see the example, the big theta notation. So we already know that the polynomial function, we can just consider its leading term x squared. So the other function is also x squared. So they are the same order. So we can say it's big theta x squared. Okay. Next, let's see how we prove big theta notation. Remember, we need to prove big O of x squared and big omega of x squared. Then we can see the results will be big theta x squared. So firstly, let's see how we can consider big O notation. We have seen this example before, right? So we can see this one is correct. And then this function is larger than x squared. So clearly it's big omega x squared. So by big O and big omega, then we can prove that f of x is big theta x squared. Okay, next, let's see if f of x is big theta g of x. Then it must be the case g of x is big theta f of x, because once we write the big theta notation, we already know that they are of the same order. So f of x is the same order of g of x. So they are big theta for each other. Okay, next one, f of x is big theta of g of x if and only if it's the case that f of x is big O of g of x and g of x is big O of f of x. Okay, because when we write g of x is big O of f of x, it means f of x dominate the function g of x. Okay, and f of x is big O of g of x, which means g of x dominate f of x. Okay, so if they are upper bound for each other, then we can see let's follow the definition of big theta notation. Next, let's see the big theta estimation for polynomial functions. The theorem tells us once we have a general polynomial function, an times x to the power of n plus an minus 1 times x to the power of n minus 1 plus a1x plus a0. So we can see this is the general form of the polynomial function. Then the theorem is f of x is of order xn. Okay, so it's big theta of x to the power of n. This can be derived by the previous example, right? We have seen that f of x actually is big theta x squared. So if we extend this to general polynomial functions, then the result still holds. So once f of x is a times x to the power of 5, then it's the order of x to the power of 5. Okay, I think this is very similar to a big O of the general polynomial function. That's the end of this section. I hope you can clarify the difference of 3 different notations, big O, big omega, and big theta. Because when you first learn this, it will be a little bit confusing. But I think if you can consider the relationships of 2 functions, which one dominates the others, so you can consider the upper bound, the lower bound of these functions. Then we can clearly determine the growth of functions by these 3 different notations. Okay, see you next time.